Welcome to our channel. Hello everyone, and welcome back to Meg Updates. Today, we have an intriguing topic lined up for you. If you're involved in computational modeling and simulation, or just curious about the latest in materials science, you're in the right place. In this video, we're diving deep into the limitations of the representative volume element, or RV, in software modeling and simulation. While RVs are a powerful tool for understanding and predicting the behavior of complex materials, they come with their own set of challenges and limitations that are crucial to understand. We'll explore why selecting the right size and shape of an RV can be tricky, how boundary conditions can sometimes skew results, and why even with advanced computational resources, capturing the true nature of a material can still be a daunting task. Plus, we'll look at how these limitations can impact the accuracy of your simulations and what you can do to mitigate these issues. So, whether you're a seasoned engineer, a researcher, or a student, stay tuned as we unravel the complexities and nuances of using RVs in your simulations. Don't forget to like, subscribe, and hit the bell icon to stay updated with all our latest content. Let's get started. A representative volume element, RVE, is a crucial concept in computational modeling and simulation, particularly in the study of heterogeneous materials. It is a small volume of material that statistically represents the properties of the entire material. While using an RV can greatly enhance the efficiency and feasibility of simulations, there are several limitations associated with this approach. 1. Size and selection of RV. Size determination, identifying the appropriate size of an RVE, is challenging. It must be large enough to capture the heterogeneities and the statistical variations in the material properties, but small enough to keep computational costs manageable. Representativeness, ensuring that the selected RVE is truly representative of the entire material, can be difficult. If the RV is too small, it may not capture all the necessary microstructural features, leading to inaccurate results. 2. Boundary conditions. Boundary effects. Applying boundary conditions to the RV can introduce artificial constraints or forces that do not exist in the actual material. This can affect the accuracy of the simulation results. Periodic boundary conditions. To minimize boundary effects, periodic boundary conditions are often used. However, these are not always applicable or appropriate for all materials, especially those with non-periodic microstructures. 3. Computational cost. High computational demand. Despite being a smaller volume than the whole material, an RV can still require significant computational resources, especially for complex materials with intricate microstructures. Multi-scale modeling. When integrating RV-based simulations into multi-scale models, the computational cost can escalate rapidly due to the need for simulations at multiple scales. 4. Homogenization assumptions. Assumption of homogeneity. The use of an RV often relies on homogenization techniques, which assume that the material properties are uniformly distributed within the RV. This assumption may not hold for materials with significant local variations. Scales separation. Effective homogenization requires a clear separation of scales between the RVE and the macroscopic material. In cases where this separation is not clear, the homogenized properties may not accurately represent the actual material behavior. 5. Anisotropy and heterogeneity. Complex microstructures. Materials with highly anisotropic or complex heterogeneous microstructures pose a challenge for RV selection and accurate representation. Capturing the directional dependencies and interactions within the material may require more sophisticated approaches. Evolving microstructures. For materials that undergo significant changes in microstructure during use, example, due to plastic deformation, phase transformation, a single RV may not be sufficient to represent the material accurately over its entire life cycle. 6. Validation and calibration. Experimental validation. Ensuring that the RV-based model accurately reflects the real material behavior requires extensive experimental validation. This can be time-consuming and expensive. Parameter calibration. The material properties and behavior within the RV need to be calibrated with experimental data, which can introduce uncertainties if the data is not accurate or comprehensive. 7. Stochastic nature of materials. Randomness. Many materials exhibit inherent randomness in their microstructures. Capturing this randomness accurately within an RV can be challenging, and a single RV may not suffice. Multiple RVs might be needed to statistically capture the material's properties, increasing computational demands. Conclusion. While RVs are a powerful tool in computational modeling and simulation of heterogeneous materials, they come with several limitations that need to be carefully addressed. Proper selection, validation, and calibration of the RV are essential to ensure accurate and reliable simulation results. Advanced techniques and methods may be required to overcome these limitations, especially for materials with complex or evolving microstructures. Thanks for watching. And that wraps up our deep dive into the limitations of the representative volume element in software modeling and simulation. We hope you found this video informative and that it gave you a clearer understanding of the challenges and considerations when working with RVs. Remember, while RVs are incredibly useful, it's crucial to be aware of their limitations to ensure your simulations are as accurate and reliable as possible. If you have any questions or comments, feel free to leave them down below. We love hearing from you and will do our best to respond. If you enjoyed this video, don't forget to give it a thumbs up and share it with your friends and colleagues who might find it useful. And if you haven't already, make sure to subscribe to our channel and hit the notification bell so you won't miss any of our upcoming videos on computational modeling, materials science, and more. Thanks for watching, and we'll see you in the next video.